ladies. In this video we are talking about buffers and ionic equations. So we're finishing up chapter 15 with acids and bases. In your chapter handout, we have the definition of a buffer. So a buffer is a substance that resists changes in pH when a strong acid or strong base is added to it. This is to a certain extent that it's going to resist changes to pH. If we add a lot of the acid, the strong acid, or a lot of the strong base, it's obviously going to affect it, but with minor changes, like additions to a strong acid and strong base to our buffer, we're going to resist the change. So buffers are made up of a weak acid and its conjugate base. So the conjugate base you might see as a salt, like we will in example number 18 and 19. But the salt is basically the conjugate base, so everything minus the hydrogen ion here with its conjugate base. So for an example, hydrofluoric acid is a weak acid. It is not in your list of the 6 strong acids that you need to know. Its conjugate base would be everything that's left over after we take away the hydrogen ion, the proton, which is fluorine. And an example of its salt would be a metal with fluorine. So lithium fluoride, sodium fluoride, potassium fluoride, or some salts that you might see for this conjugate base. We could also see so buffers can also be weak bases in its conjugate acid, but for our purposes, for the chapter handout, we're talking about a weak acid and its conjugate base. Okay, so basically how this works is that our buffer is going to soak up additional hydrogen ions that are causing those changes in pH. So pH, we are looking at the amount of hydrogen ions in our solution. So if we have a high pH, so something that's basic, we have fewer hydrogen ions. If we have something that's acidic, we have a lot more hydrogen ions, so we have a lower pH. So in Canvas, there is a link to a YouTube video. I think the link for the video in Canvas says buffers-blood buffer system. So buffers are explained in a good analogy in that video. So watch that video if you need a little bit more information on buffers. And buffers are super, super important to keeping us alive in our blood. So watch that video. It's super interesting. Okay, let's look at example number 18. So which of the following, when added to water, so in solution, can act as a buffer system? So we're looking for something that is a weak acid and its conjugate base. And in these ones, we're having some type of salt. So hydrofluoric acid is a weak acid, and sodium fluoride, like in my example down here, is its salt. We just have the hydrogen ion minus the hydrogen ion plus some metal. So a weak acid and its salt, it can act as a buffer system. So yes to A. Nitric acid and potassium nitrate. Nitric acid is a strong acid. It is on your list of the 6 strong acids. So it cannot act as a buffer system, only a weak acid with its conjugate base. So this is a strong acid plus its salt, but strong acids cannot act as buffer systems. All right, and then C, we have ammonia and ammonium chloride. So ammonia is a weak base. So let's look at where our proton, like if we are gaining or losing a proton. So we have NH3 and NH4 here. So we're gaining a hydrogen ion. So that means that if we are accepting a hydrogen ion, we're going to be a Bronsted-Lowry base. So ammonia is a base, which means that ammonium chloride is its salt. So yes, it can act as a buffer system, but because for our chapter handout purposes, we're going to say no. But yes, it technically can. But let's be consistent with the chapter handout. Okay, so example number 19, we're doing the same thing. So which of the following can act as a buffer system? So letter A, hydrochloric acid is a strong acid. Sodium hydroxide is a strong base. Neither of those are a weak acid in its conjugate base, so nope, not A. All right, let's look at letter B. So we have seen this guy written quite a few different ways, but for our intents and purposes, we are going to write it as this. So we're writing this guy as this. This is acetic acid. You have definitely seen that quite a few times and written quite a few different ways. But we got our hydrogen out in front, so that is acetic acid, and that is a weak acid. It is not on our list of strong acids. Sodium acetate is its salt. So we got a weak acid, conjugate base, we can act as a buffer system. So yes to B. All right, last one, let's look at C. So hydrobromic acid and potassium bromate, strong acid with its salt. It is not a weak acid in its conjugate base. So watch the blood buffer system video that is linked in Canvas to give you like an analogy about buffers and to show you how important they are in our body to keeping us alive. Because your blood pH can act within such a small range. It's like 7.3 to 7.4. And if your pH of your blood goes out of that range, you will die. It will do damage to your organs, and you will die. So buffers are super, super important to keeping us alive. So watch that video. Okay, net ionic equations is the last thing we need to talk about. So with net ionic equations, we are talking, we're going to be showing the equation that involves only the substances undergoing a reaction in solution. How we know that a reaction occurred on paper is if we see a state of matter of a solid, liquid, or gas. If we're in the lab, we could see a color change. We could feel if there's a temperature change, either if it's getting warmer or colder. So exothermic, endothermic. But on paper, the only way we know a reaction occurred is if we are producing a solid, a liquid, or a gas. So the net ionic equation is showing the aqueous ions that are involved in making our solid, liquid, gas product. There are 3 rules that we're going to be following when we write these guys, these net ionic equations. The first step, we are going to complete and balance the chemical equation. Second step is we are writing the complete ionic equation by ionizing substances that are dissolved in water. That means if it is aqueous, we are writing out, we're separating out our compound into its ion, so cation, anion. And then we are not touching the gases, liquids, or solids. They are staying together. We are not separating them out. Only aqueous solutions are getting separated out. All right, and 3, cancel spectator ions to obtain the net ionic equation. Spectator ions. If you are a spectator at a sporting event, you are watching the game happen. You are not playing the game. So the net ionic equation is describing the players in the game, or the ions involved in making a product. The spectator ions are everything else that is not involved in making our solid, liquid, or gas. So we'll explain that a little bit more when we work through these right now. So let's look at number 20. So number 20, we're writing the net ionic equation for the reaction between aqueous solutions of nitric acid and barium hydroxide. So in this problem, we are just given the reactants, the names of the reactants. So I've already written out what these guys are, their molecular formula from their names. This is going back to, I believe, chapter 8, where we were talking about chemical reactions and writing a chemical equation from the names of our reactants. So nitric acid, it's an acid, so we have a hydrogen out in front. We have an ic acid ending, so that means we had an 8 ending in our polyatomic ion, so NO3 is nitrate. So HNO3 is nitric acid. Barium hydroxide, barium is a positive 2 charge. Hydroxide is OH minus 1. So we're crossing our charges, and we get 2 outside our parentheses for hydroxide. All right, our molecular equation. So remember when we are writing our molecular equations from our names, we need to cross our names. So here we have hydrogen nitrate, if you want to think about it like that. This is barium hydroxide, so we're going to keep the hydrogen the same here and then just change the second part of the ending. So we have hydrogen hydroxide, which is water, and then we have barium nitrate. So these two guys are teaming up. So double replacement reaction. Nitric acid, barium hydroxide is going to make water, which is a liquid, so we need that, that's important. And then our salt is barium nitrate. This is not a solid, that is aqueous. My bad. Okay. So then we are going to balance our chemical equation. We get 2, 1, 2, 1. So we start with aqueous solution. So these two guys are aqueous. And then water is a liquid. Aqueous means it's dissolved in water. So if it's water with itself is just a liquid. And then barium nitrate, anything with a nitrate attached to it is soluble in solution. So it's aqueous. So the only thing that's telling us a reaction occurred is that we're making water. All right, complete ionic equation. So we are separating everything out into, so separating everything that's aqueous out into its ions. So here, this coefficient is being distributed into all of those ions. So we have 2 hydrogens, and that's going to be aqueous because it comes from an aqueous compound. We have 2 nitrates, that's aqueous, it comes from an aqueous compound. Barium plus 2, aqueous. We have our hydroxide ion, aqueous. We are producing water, so 2 of them. And then we're keeping that together because it's a solid, liquid, or gas. So we are not touching them. We are not separating out our ions. Ba plus 2, barium ion, is aqueous. And then we are producing 2 nitrate ions. So we're putting that 2, the subscript, into a coefficient. So just moving it up front. And that is aqueous because it came from an aqueous substance. So with our complete ionic equation, we are writing our ions. And we are leaving our product that we're making, the solid, liquid, or gas. Okay. With our net ionic equation, we are going to be canceling out spectator ions. So anything not involved in making our product. So anything not involved in making our liquid. So hydrogen shows up in water. Nitrate does not show up in water, so let's cross it out. Barium does not show up in water, cross it out. Hydroxide does show up in water. You can rewrite this as HOH. That is still water. That shows up in water. Barium, again, does not show up. Nitrate does not show up. So we're crossing out those spectator ions. They are not involved in making water. So that means our net ionic equation is everything that is left over, so the hydrogen, hydroxide, and water, simplified down. So here we have 2 hydrogens, 2 hydroxides, 2 waters. So we're going to divide by 2, and we get 1 hydrogen ion, aqueous. Sorry, I forgot them in my notes. 1 hydroxide ion, aqueous, and we are making 1 water molecule, and that's a liquid. So make sure for these ionic equations, you have the ions, positive or negative charge, and their state of matter, aqueous, aqueous, and going to either a solid, liquid, or gas. All right, let's look at number 21. So we are writing the net ionic equation for the reaction between aqueous solutions of silver nitrate and aluminum chloride. So first we have to write the molecular equation. So silver nitrate, silver is a positive 1 charge, nitrate is NO3 minus 1. So they cancel each other out, so we just have AgNO3. It's aqueous because it tells us that it's an aqueous solution. Aluminum chloride, aluminum has a positive 3 charge in solution, chlorine has a negative 1 charge in solution. So we have AlCl3 in order to cancel out our charges. Silver chloride Ag plus 1, Cl minus 1, they cancel each other out, AgCl. That is a solid. If you are to check your solubility charts in chapter 8, you would find that silver and chlorine make an insoluble compound, so it's staying a solid in solution. And that's important because we know a reaction occurred. And then aluminum nitrate is our other product. So aluminum is plus 3, nitrate is a negative 1, so we need a 3 outside our polyatomic nitrate. And that is aqueous. Anything attached to a nitrate is aqueous, soluble in solution. Our next thing we're doing is the complete ionic equation. So we are separating out anything that has an aqueous state of matter. And we are leaving our solid, liquid, or gas together. So here, again, I've forgotten my states of matter. This 3 gets distributed into the silver and the nitrate. So this is 3 Ag plus 1 aqueous ions, 3 NO3 minus aqueous ions, plus 1 Al plus 3 aqueous ion, 3 Cl minus 1 aqueous ions. Those all come from aqueous compounds, so they separate out. We are not touching our solid, liquid, or gas. It stays together. That is how we know a reaction occurred. So we have 3 of those after we've balanced our chemical equation. So we have 1 aluminum Al plus 3 aqueous ion, and then 3, because we're bringing that subscript out front to be a coefficient, 3 NO3 aqueous ions, and that is the only one I wrote, apparently. Okay, at this point, we are crossing out any of our spectator ions, the ones not involved in making silver chloride. So silver is in silver chloride, nitrate is not, cross it out. Aluminum is not in silver chloride, cross it out. Chlorine is in silver chloride, so cross out aluminum and nitrate on the other side. Everything that is left over is in our net ionic equation. We need to simplify our coefficient, so 3, 3, and 3 are going to simplify down to 1s. So here we have Ag plus aqueous ion. Chlorine minus 1 aqueous ion is going to make silver chloride solid. At this point, you can do the net ionic equations worksheet, and that is the last worksheet in chapter 15.